Hi, this is the Chapter 4 lecture for Chem 7, and we're going to talk about how to name things in chemistry. So formulas we've talked about before is the ratio of the two atoms together, and when they're ions, it's called an ionic compound. So the formula for ionic compounds are the metals listed first, the one on the left side of the periodic table, and then the one on the right side of the periodic table is named second. So for example, sodium's in group 1, so it's named first, and chlorine is group 7, so it's labeled second, and it's named second. And so we call the first element, it's just regular name from the periodic table. And the second ion that's in the formula is changed from chlorine to chloride. So you have sodium chloride, and you've probably seen fluoride in your toothpaste. So we always change the second element, the one that's on the right side of the periodic table, into "ide" when we're talking about two elements together to make one compound. The formula, so that's for ionic compounds, and the formulas for molecular compounds have a different way of naming, and so we'll talk about that as well. And remember, molecular compounds are elements that are close together on the periodic table, usually on the right-hand side. So formula units is just how the 2 or 3 or 4 ions come together in one unit and make 0 charge. So chlorine has a -1 charge and sodium has a +1 charge. So they go in a ratio of 1 to 1 to make that 0 charge. We don't want any charge to be left over, so we have to get them to 0 out. And so the formula unit for ionic compounds is the simplest ratio of positive to negative ions to make a 0 charge. Molecular compounds are put together by how they bond together. And so we can show a molecular formula like H2O. We can show how it makes a structural formula in 3 dimensions, but we have to draw it on a flat piece of paper, so that's called the structural formula. And then the space filling model shows how the atoms hook together in more of a 3-dimensional kind of way. So molecular formula is more like a shorthand way of saying it. Structural is kind of talking about its shape, and space filling is really 3-dimensional. So we can talk about them and show them in 3 different ways. So for binary ionic compounds, we have a positive metal, cation, and a negative metal, anion, and they're from the 2 sides of the periodic table. The name consists of the cation plus the anion, and we know that all these ions have charges. So remember, group 1A's have a +1 charge, and group 2 has a +2, and group 3 has a +3. So these are fixed charges that I was telling you about on the periodic table that we should label all the A's with their charges. That's one kind of cation, and then there's another kind of cation that has can have variable charges, and those are those elements in the middle of the periodic table. The transition metals can have different numbers of charges on different types of ions, so they're a little bit more tricky and complicated. So when we're doing binary ionic compounds, these are the ones that have fixed charges, like group 1 is always +1 and group 2 is always +2. And we put them together so the charges balance out and make 0. And we have the first name of the first element, its regular name, and then we change the negative ion to an "ide." So the second one is always changed from its regular name into an "ide" form. So sodium sulfide instead of sodium and sulfur. Sodium sulfide when it's in a binary ionic compound. Binary means 2 atoms are put together. 2 types of atoms are put together. So remember, non-metal anions have charges based on their group number. So group 5 wants 3 more electrons, so they become -3 ions. Group 6 wants 2 more electrons, so it becomes a -2 ion. And group 7 wants 1 more electron, so they become -1 ion. So remember to label that on your periodic table. Now some ions, like the metals, the transition metals in the middle of the periodic table, can have more than one charge. So for example, these are called group 2 cations. For example, iron chloride, let's look at their charges. Group 7 guys always are the same, so chlorine's always a -1, and I have 3 of them, so that makes a -3 on the right-hand side of this compound. So if this whole side is -3, and I have one Fe, then the Fe has to be a +3. So it's going to be iron is going to have a +3 charge, and chlorine is going to have a -1 charge. Let's look at iron in this situation. Oxygen's in group 6, so it needs 2 more electrons for each one. So it's going to be oxygen -2, and I have 3 of them, so I'm going to make a -6 overall for the oxygens. In this compound I have 2 ions, so to make a -6 and to have 2 ions, each one of them is going to have to be a +3. Now when we are using these variable ions that can change their charge, we have to tell you what the name is, because otherwise you're not going to know. So when we name it, we have to say what charge it has. So these Roman numerals are telling you the charge. So Fe2+, we say iron 2 ion, that means it's got a +2 charge. Iron 3 ion has a +3 charge. So we use Roman numerals in the name to tell you what the charge of the metal ion has, the first ion in that compound. So when we do these guys who are variable in the center of the periodic table, the transition metals, they can have different charges depending on the situation that they're in. So we have to tell you what their charge is by using Roman numerals. So type 1s, they don't change their stripes. They're like tigers that don't change their stripes. They always have the same charge. So aluminum on the left-hand side here has a +3 charge, and bromine always has a -1 when it becomes an ion. So to make that 0 charge, we need 3 negative guys. We need 3 negatives to balance out the +3. So that means the formula is going to be AlBr3 to make everything balance to 0. Type 2, remember we have to tell you what the charge is for this guy. So this copper, in this instance, is a +2 charge. And we need to balance out with the -1 charge. So that means we better put 2 of these bromines in this formula to balance out that +2 charge. You're going to need to memorize some things called polyatomic ions, and they're going to help you a lot when we make formulas. And sometimes I'm just going to give you the name, and you're going to have to know what it is. So please memorize this list. Ammonium ion, for example, is NH4+. Acetate is C2H3O2-. So just make some flashcards with these, or memorize them however you'd like. But we will be using these, and it'll be really helpful if you have these memorized. They're called polyatomics because this whole chunk has a charge overall. So, for example, ammonium formula is NH4, and overall that big chunk has a +1 charge. So that remember the numbers down below are how many atoms I have of hydrogen. But this number here is the overall charge of that chunk, that polyatomic ion chunk. So these we pretty much named the same way, but we're going to use that name of it, so that really helps you if you have these memorized so that you can put these together. So for example, if we have Fe3 plus and we have sulfate, which the whole chunk has a -2 charge, I'm going to swap these two like we've done before, but I'm saying that I need 3 of these chunks, so I better put this whole big chunk in a parentheses so that it makes more sense. So when you have polyatomics that you need more than one of, you got to put it in parentheses so we can see how many you need. Same thing here. This has a 4+ charge for this lead, and this chunk has a -1 charge. So if I swap the charges, I'm going to put a 4 on that chunk, and I better say that I need 4 of them. So put this whole chunk in parentheses and say, hey, I need 4 of those chunks. When we name covalent things, remember ionic things have charges, but covalent things are bonded together, they're sharing their electron clouds, and we name them differently. So covalent things are named using these prefixes. And so we need to know these as well. So start memorizing your covalent compound prefixes. For example, if you have 1 of something, that's called mono. If you have 2, we have di, so forth. And we only use that mono for the second element. So I'll show you some examples of that. So for example, this carbon monoxide, I don't say monocarbon monoxide. I just say carbon, first guy, and 1 oxygen hooked to it. So we try to make it a little simpler by not saying monocarbon monoxide. So on these are compounds that are together. These are atoms that are sharing their clouds. And we do the same thing where we, the second element, we call it an ide. So we say this one has 2 nitrogens, so we say dinitrogen. Has 5 oxygens, so we say pentoxide. So we'll do practice problems in class. And we're also going to talk about chemical equations in this lecture. So when we have a chemical reaction, that means that molecules or compounds are rearranging themselves into something new. The things that we start with are called the reactants, and after the chemical reaction, they're called the products. So we use a chemical equation to show reactants and products, and other things as well. And it's a really shorthand way of saying what actually happened in the beaker that you are doing the chemical reaction with. So this is showing a chemical equation, and this is explaining a chemical reaction. So for example, if I have methane, which is something that's you're able to burn, and I have it in an atmosphere of oxygen, it can form carbon dioxide and water. This is called a combustion reaction, and it would really be good if you memorize this reaction. We have a fuel, which is the methane. It has to be in the presence of oxygen. These are the reactants. Then I draw an arrow, and I make products, carbon dioxide, and I make water. So those are all things that you need to have in a combustion reaction. You need to have a fuel, you need to have it in the presence of oxygen, and when you're done, you're going to make carbon dioxide and water. So when you're driving your car to LMC, you have a fuel which is octane, the gasoline in your car. You're burning it in oxygen, and you're forming carbon dioxide and water out of your tailpipe. When we do these chemical reactions, we have to show that we're not magically appearing or disappearing atoms. So we have to balance the equation so that all atoms are accounted for on the left side and the right side. It's just like an accounting problem. So on the left side, I'm saying I have 2 nitrogens reacting with 6 hydrogens. So 3 times 2 makes 6 hydrogens. And on the right side, I have to have the same amount because they can't magically appear or disappear atoms. They have to be accounted for at the beginning and the end So at the end I have 2 nitrogens and 6 hydrogens, so this balances. So if you notice I have a 2 in front of the ammonia, so 2 times 1 nitrogen is 2, and 2 times 3 hydrogens is 6. So that balances. We'll do practice problems in class. Another thing we need to talk about in this chapter is the mole. And moles are ways of counting things. This concept kind of bothers people, so I need you guys to really pay attention to moles, and we'll do a lot of practice in class. But moles are just a way of counting things. So they're a way of counting really small things. We can count atoms, molecules, ions, electrons, pretty much anything. And when in real life we count things in units called dozens or cases or 12 packs or all different types of things, in a gross and a dozen and things like that. But in chemistry we called our counting unit a mole, M-O-L-E, and it's just the same idea as a dozen. Instead of going to Krispy Kreme and getting 1 donut at a time, maybe you need to get it for your office, and so you buy 3 dozen, which is 36. So instead of going and buying one donut at a time, you buy a big quantity of them. So same thing with atoms or electrons or moles. We can go and get a big quantity of them. So we use a number that bothers people, but it's just a number, so don't let it bother you. We use this thing called Avogadro's number, which is a guy who figured this out. And so he figured out that we're going to call this counting unit a mole, and it's 6.022 times 10 to the 23. It's just a number. It just means 6 followed by 23 zeros. So it's a big number, but it is just a number, so don't let that throw you. And we can use it for math, of course. In chemistry, we love math. So if I have 3 moles of sodium, I can change it to how many atoms that is, just by multiplying 3 times the Avogadro's number of 6.022 times 10 to the 23rd. And so we'll get used to this. That's why I had you guys practice scientific notation, because we'll use this a lot in this section. If I want to change the number of atoms I have into how many moles I have to divide by that number, 6.022 times 10 to the 23rd. So we'll practice this a lot, but this is something you have to get good at, because we use it quite a bit. Numbers of moles. So the nice thing about the periodic table, I told you it tells you a lot of things in one piece of paper. For example, if we have 1 mole of copper, we can just look at the number at the bottom of the periodic table, the 63.55, and know that 1 mole of copper atoms would weigh that many grams. So they call it the atomic mass. So if you're just looking at one atom, one atom is 63.55 AMU. If we look at 1 mole, it is 63.55 grams. So it's really nice because they made it simple. You can get the mass of 1 atom, or you can get the mass of 1 mole with that number. So we can change moles to grams as well. So if I have 3 moles of Na, I just look at the periodic table and it tells me at the bottom of the square that 1 mole weighs 22.99. So if I multiply those together, I get the mass of 3 moles. And I can go backwards too. If I have grams, I can figure out how many moles that is. So I can take the 55.2 grams, divide by 32.1 grams for sulfur, and I know how many moles I have. So I can go back and forth. So we have to get good at these type of problems. So if we're talking about ionic compounds, we have a formula mass. It's the mass of one of those formulas. If we have a covalent compound, we just call it molecular mass. So don't let those throw you. We're just looking for the mass of the compound. And we can change moles to grams and grams to moles. So if we need to find the molar mass of a compound, it's not on the periodic table, but we can still use the periodic table to find it. So I will look for the mass of hydrogen, and I'll look for the mass of oxygen, and I will put those together to get the mass of 1 mole of the compound. So for example, hydrogen weighs 1.01 grams. In water I have 2 of them, so I multiply by 2. And I have 1 mole of oxygen, so I find the mass of that on the periodic table and I add them together. And so altogether, 1 mole of water would be 18.02 grams. There's one of these types of questions on the unit tests, so I want to make sure you guys know how to do these. When we have a balanced equation, we can figure out if we know we either know grams or moles of a reactant or product, we can figure out every other mass or amount of moles of everyone else in the balanced equation. So first step is you always have to balance them. Then you can figure out the ratio of the moles to each other. For example, in this balanced equation, there's 3 moles of H2 to every 1 mole of N2. There's 2 moles of ammonia, NH3, to every 1 mole of N2. And there's 3 moles of H2 to every 2 moles of NH3. So the balanced equation tells you all that stuff. So we can figure out how to go from moles of one thing to moles of another using that ratio. So if I know that I want to start with 8.5 moles of N2, and I want to know how much hydrogen I need to put in that container to make it react completely, I can figure that out with this mole ratio. I can also figure out grams. So if I know grams of one thing, I can convert it to grams of something else in the balanced equation. So first step is always balancing. So for example, if I have 35 grams of nitrogen and I want to know ammonia, I can figure out how many grams is how many moles of nitrogen, the ratio of ammonia to nitrogen, how much 1 mole of ammonia weighs, and then I can figure out the grams of ammonia I'm going to produce. This is really helpful for those folks who are making a new compound out of reactants. So those folks in P-Tech, this is what you got to know all the time. How much you're putting into your reactor and how much you should get out of your reactor. So we'll do practice problems in class, and that's it for this Chapter 4 lecture, and we'll talk more about this in class. Thanks for watching.